So I want to lead off here talking about our upcoming schedule. So this is where I have us now. We just finished gas laws, and so you should have a lab that you can turn in on that. Remember that you're writing it up like a journal article, and you're just replacing bits in there, kind of the prefab thing that I did for you. So then we'll follow that up with the airbag lab this week. A lot of folks have a lot of fun with that one. Hopefully it's more on the design phase and tickle some of your fancy on the idea of coming up with your own procedure and stuff there. So lecture side, we'll talk about phase diagrams here in this lecture, and then what we have left before the exam are solubility, and then we'll talk about solution phases. It talks more about phases today. And then we have colligative properties. And after colligative properties, I am looking at exam 1. Now I know this pushes us back to mid-September before we have exam 1. And the others will come more quickly after that. But what this does is it allows us to brush up that stoichiometry and stuff. Just please do remember that stoichiometry is still a main thing, biggest thing that you should have brought from Chem 1. And it will always be an issue on exams. So moving on into the phase diagrams, and I wanted to tie this back to things that you do already know about. So don't be put off by this being a big two-dimensional representation of things. I'm going to try to make it make sense compared to what you've already experienced or known throughout your prior experiences. So to keep things relatively simple on this diagram, we're going to talk about gas here as a phase, liquid here, and then this solid phase here in the blue. Now, here I'm using phase as opposed to state. We'll see later how I can have multiple different solid phases. There are ways to have different phases in a liquid, although that's more difficult. But you can have different phases within what we typically refer to as states. Go back and review that in the previous lecture if needed. But here they are at least physically separable, so we can also refer to them as phases. So these lines in between, for instance, here I've got this curvy line in between solid and gas, and then I've got this curve in between gas and liquid, and I've got this looks like a relatively straight line, but it's probably still some curvature to it, between solid and liquid. Okay, so those lines are called phase boundaries. Okay, so there's a phase boundary here between solid and liquid. And so they're like a graph, they're like a line on this graph with temperature plotted on the x-axis and pressure plotted on the y-axis. And so certain areas we delineate on this graph, and this phase area is the area that corresponds to solid behavior. And this phase area in blue and purple here corresponds to the idea of a liquid. In this brown phase area, higher temperature and lower pressure, say lower on the y-axis but higher on the x-axis, that corresponds to a gas. But if you take a given temperature and you move to a higher pressure, even without changing the temperature, you can cross the phase boundary and go from gas behavior to liquid behavior. Okay, now let's talk about what these transitions, what terms we hang on these transitions. So if you go from a solid to a liquid, we call that melting. If you go from a liquid to a solid, we'll call that freezing. Now, of course, you've already seen that. It surprises me sometimes how this gets folks. If I ask you what is the boiling point of H2O, then a lot of folks will be able to tell me that it's 100 C. But if I ask what's the condensation temperature at 1 atmosphere for H2O, fewer people will be able to tell me that that is also 100 C, because they don't connect these two processes as being backwards. So melting is the same boundary on the pressure temperature diagram as freezing is. So for a given pressure, that happens at the same temperature depending on which direction you're going. Same thing for vaporization or boiling, and then condensation, which is going backwards from gas to liquid. Maybe a little less familiar to you here, you can go straight from a solid to a gas. You might have seen this in the form of CO2, dry ice we call it sometimes, CO2 solid, can sublimate to form a gas, CO2 gas, without going through a liquid phase. The reason is because it doesn't ever cross into the liquid phase area on the diagram. Going the other direction is called deposition, from gas directly to a solid. So you should be familiar with those terms and how they relate to each other. Now, here I have this note that Tm, and I mean melting temperature, but you could also say T vaporization or whatever, any of the temperatures are dependent on pressure. So, for instance, if I say that the boiling point of water is, let's say, a certain temperature here, 100 C. I know there's no scale down here, but just say it is 100 C. Well, that depends on what pressure you are looking at. If you increase this pressure, now suddenly my phase boundary is at a different temperature point also. So if I increase the pressure from 1 atmosphere to some greater number, 5 atmospheres or whatever, I would expect the Tm, or Tb in this case, the boiling point, to be higher than 100 C. Another thing got two more things I want to point out on this. So this is labeled as a critical point up here. So I think I'm going to talk about this in another slide also, but this point is kind of where our phase boundary sort of becomes indistinct, and beyond the critical point you can't tell a gas from a liquid very easily. In fact, we just call it a supercritical fluid. There's also this, the triple point we'll talk about, and it is a point where all three, solid, liquid, and gas, are stable at the same time in contact with each other. So dynamic equilibrium idea, and we'll talk a lot more about equilibrium in Unit 2 of this course, but the idea of equilibrium, chemistry is statistical. So if I say that a material is in a solid area on the phase diagram, it does not mean that all of the material, I guess liquid would be a better example to use here because I've got liquid in this diagram. So start over and say if I say that a material is in the liquid area of the phase diagram, right? It doesn't mean that no molecules are transitioning from a liquid behavior to a gaseous behavior. We know that they are, but we just think that there can be an equilibrium where you only have a little bit in the gas phase versus most being in the liquid phase here. So here's my temperature gauge on this. If I increase this temperature, well, now I have more of an escaping temperature for these liquid molecules wanting to become gas phase molecules. And so more of them than had been go and get in the gas phase as opposed to the liquid phase. Well, what that does is it changes the amount of material that wants to be in the gas phase until a new equilibrium is reached. And so we can determine what's called a vapor pressure, determined based on what proportion of our molecules want to be in the gas phase as opposed to the liquid phase. And that is dependent on temperature. So here are those critical points again, and so looking up here, you can see that so we call both gases and liquids, we call fluid. because they move very easily under influence of differential pressure. So both are fluid, but above this point in the pressure temperature region here, you can't really tell one type of fluid from another type of fluid. And so we just call it a supercritical, meaning beyond critical fluid. So it is still a fluid, but we can't tell really whether it's a liquid or a gas anymore. And here's that triple point. For water, the triple point is at 0.01 C, so almost the 1 atmosphere freezing point. But look here, it's the pressure. The pressure is very, very low for the triple point of water. So remember, this is our normal atmospheric pressure is about 101 kPa. So this pressure is down at 0.6 kPa. So what's happened? So as we decreased, as we brought the pressure down, so remember that it is a function of both pressure and temperature. So here's our normal point at 101 kPa, right? We expect the boiling point of water to be 100 C. But if we decrease that pressure, it makes it easier for those liquid water molecules to go get in the gas phase, right? So that brings the overall temperature required down. So by decreasing pressure, I'm dragging the temperature down with it, right? So I'm making it less and less required temperature down to here at 0.6 atmospheres. I'm sorry, not atmospheres, 0.6 kPa. It's very, very low pressure, 600 pascals pressure. The required temperature to boil water is only 0.101 C. But now, similarly, if you look at the freezing, thawing, freezing, melting line here, right? It is pressure temperature, but related to both. Also, it's not as temperature dependent, so the temperature doesn't change as drastically as you change the pressure, but it does change some, and so it reaches this spot. And then below that temperature, and especially below 600 pascals, you get into this range down here where water, ice, can act like CO2 ice and go straight from sublimation here, straight from the solid to the gas phase, skipping the water phase entirely, the liquid water phase entirely, because you're in this region down here. So be able to tell what's going on. I know that our exam has some questions on it where you've got to tell me what's going on. As you cross these boundaries, you've got to take a given pressure and temperature and be able to tell what's the equilibrium phase under those conditions. Now, I'm about to go and talk more about the solid phases. So if you need to review about there being separate phases within the solid state, review that, and that's where we're going next. From last lecture, I mentioned this idea of crystalline versus amorphous solids. So amorphous solids their atomic centers are kind of locked in place. These guys can't move around very much. They're locked, but they're not in what we call a lattice structure. They're not in this regular array like this. So this one over here on the left is crystalline because of this regular array of atomic centers, while this amorphous one might have the same chemical formula, but it doesn't have the lattice pattern, and that's important. You could think of this, you probably have heard of glass being SiO2 and also quartz being SiO2. Well, both have the same chemical formula. They're the same. If we break it down in the ICP, we're going to get the same results. However, quartz is different because it is crystalline, because it has a lattice, and amorphous glass does not have. Also mentioned last lecture about carbon allotropes and how you can have this. So this is basically a tetragonal system where you have carbons linked in this tetragonal pattern. You have this 3D network, and it's super duper strong because of that networking of carbon. Well, so the formula for diamond is just C. Those are all carbon atoms. The formula for graphite is also just C. The difference in the hardness of diamond being 10 and the hardness of graphite. And it's going to get more complicated. The hardness of graphite being a 1 is because the graphite is only held together, these sheets are only held together by, linking back to our last lecture, by the dispersion forces. Some people would say here pi stacking, but that's beyond the intent of this course. We'll just call them the London dispersion forces between the carbons on this sheet and the carbons on this sheet, because obviously these are all carbons, these are all nonpolar, right? So that's all that's holding these sheets together, is those very, very weak intermolecular forces, dispersion forces, while here in diamond we have covalent bonds holding all this structure together in 3 dimensions, and so it becomes extremely hard, the hardest of minerals, a 10. Now, I do want to point out, however, if you look closely enough, these 6 carbons, now we're looking down on a pattern here, and there would be repeating rings all linked together, and you actually get a resonance structure in here. But these are very, very strong covalent bonds, and in fact, each one of these bonds is about 1.5 times stronger than these bonds. So graphite's really super low hardness technically is only in the direction of shearing these sheets off. If you're trying to break this structure, it's extremely difficult to break, even harder than breaking the diamond structure. Looking a little deeper into the silica phase diagram. Now let me point out, let me make sure that this slide does not scare you here. The different mineral phases of quartz, or of SiO2 I should say, really, are beyond the scope of this course. I'm just trying to use this to give you insight into how phase diagrams work. Do not expect to have to tell me different phases of SiO2. That is well beyond the scope of Chem 2 class. So just use it as, and I thought there would be interesting examples for some of y'all. So this red area over here is liquid. So that's where my SiO2 is liquid. This is often referred to as magma or lava if it's on the surface, right? So here we have liquid silica, right? Now, quartz, which is both of these alpha and beta, and that just has to do with the direction of rotation of the lattice. But both of those are what you would normally refer to as a hexagonal quartz crystal. Okay, so that's our regular SiO2 quartz crystal. But look here, you can have a super low temperature polymorph, cristobalite, and another one, tridymite, and these often form in like void spaces in lavas, especially by gas deposition and stuff like that. I actually put you some pictures in here. So instead of the typical hexagonal quartz crystal, look at this tetragonal here. Almost looks like an 8-sided die, right? You have this system where that is SiO2, just like quartz is SiO2, but has a very different crystal structure. And this is tridymite with these platy. They look hexagonal to me, and I'm not sure if they are, but they definitely don't look like a quartz crystal. But now up here, now we're talking about much higher. Now be careful of the scale here, because remember that we're at 100 kPa is our typical atmospheric pressure. But now look, this pressure here is in gigapascals. So the 2 here is not 200 like we're used to, but 2,000 kPa, 4,000, 6,000 kPa. So this is extremely high pressure systems, and most of the temperature. You get something called coesite here, and we don't have really good pictures. I did give links if anybody wants to read further, but remember, it's beyond what you're going to need to know for this course. And then at the very highest temperature, like meteorite impact stuff, we have stishovite, where you get these patterns of crystals. But just so the main takeaway from this should be that even something as familiar as SiO2, which we think of as a quartz, can have different bits on the phase diagram. I would also point out that our amorphous is not on this diagram, and that's because it has to, this assumes that you've reached an equilibrium, and the amorphous is really never at equilibrium in the SiO2 system. So if you have amorphous silica like opal, as in a gem, opal is not stable, and eventually, we think, and there's articles out there about this in the geology literature, but we think that it eventually will revert to a version of quartz, depending on what its pressure and temperature regime is. And that selection process depends on, well, where is it on this phase diagram? And you follow the pressure and temperature, and you say, well, it's beta quartz or alpha quartz, or depending on which one you're in. Okay, so a couple of terms here. So we talked about the lattice concept a little bit, and I want to point out how the lattice works. Now, I guess theoretically this should be in your Chem 1 material, but it's kind of at the end, and it sometimes gets glossed over a bit. So I wanted to point out this idea of a lattice, a crystal lattice. So I could talk about a formula unit of SiO2, and it would be technically incorrect to say a molecule of SiO2, right? Because if I talk about a molecule of acetic acid, I can look and find an individual acetic acid molecule that's floating around by itself. But I can't really, in a, let's say, a quartz crystal, find an SiO2 that's floating around by itself, because it'll be in a lattice pattern, so that the SiO2 is actually in coordination with more silica and more oxygens. The ratio will be 1 silica to 2 oxygens, but they're all linked in a near infinite. You see how this kind of just, and I should have like dot 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 going off here into infinity, because you could have this lattice stretching to only limited by how much material you have. Remember, we're talking on the atomic scale here, so this is like super high numbers of these, 10 to the 23rds, obviously. So so that's this formula unit is when we break it down to basically the empirical formula, and our unit cell is the volume occupied by that unit. For my chemistry majors, this idea that I'm only just touching the surface up here is going to come back in a course that you're going to eventually take called inorganic chemistry. So this will be a good place to look back and refresh lattice stuff and phase diagrams when you get to inorganic. Another term is lattice energy, and this is, it's kind of like heat of fusion, and so I saw this in the slides and thought I better look to see where that is, and it's coming in a few slides. So we're going to talk about heat of fusion also. So this has nothing to do with nuclear fusion. We're talking about a chemical process. Lattice energy is where something loses thermal energy as it locks into that rigid crystalline lattice, and it tends to be an exothermic process. This slide is just for fun. Again, it is beyond the scope of this course, and you would see it again in inorganic, or I first saw this in a course called mineralogy over on the geology side. But you can have these different types of crystal lattices, and this has to do with their symmetry system. So my math majors might like the idea that symmetry matters this much in chemistry. We don't talk about some of those connections enough, I think. But some of these are fun to look at and how they work. And I talk about how we use these crystal lattices in the next slide. So this is fun work. This is cool stuff to use here. I'm kind of a analytical geek sometimes, right? So this is how we determine those crystal lattices with what's called XRD, which stands for X-ray diffraction. So XRD measures the angle that X-rays are hitting your crystal, right? This is your theta here, and then it has a detector that also sits at an angle, and what you measure is the two, we call it 2 theta because it's really measuring it twice, but you're measuring the angle of incidence versus diffraction, right? And what's happening with diffraction is, if you think back to Chem 1 when we talked about what's called constructive, I'm trying to be clear saying that, constructive interference versus destructive interference. Only when these wavelengths line up a certain way will the beam come out coherent, in which case, if it's coherent, the peaks line up with the peaks and the troughs line up with the troughs, and you get this constructive interference. I guess up here they're showing constructive. Yeah, the troughs line up, the peaks line up, but any other angle you do not. You have to have this perfect angle. Any other angle, then you get a destructive interference, and you get next to zero signal. Well, you can use what angle work to get your constructive interference in order to work out what this distance, we call it the D spacing, what that D spacing is in the crystal lattice. And so you can see different signals, and you can start to work out different lattice direction, D spacing, and work out the overall crystal lattice that way. A couple of more connections that we might make from this phase thing. One of the things being talked about in what's called the greening of chemistry. So in chemistry, one of our big hazardous waste concerns is using all the organic solvents that we do to do some of the chemistry experiments that we do. Well, one of the approaches that's being talked about is doing experiments with pressurized CO2. Now, if you take pressurized CO2 and you liquefy it, or better yet, past that supercritical point, the critical point that we talked about earlier, you get into a supercritical fluid, and it's not really high temperature. See, we're talking 31 C right now. The pressure, though, is pretty high. We're talking 73 atmospheres. That's actually pretty drastic. But if you can do it, and you can do your experiments in liquid CO2, well, that's a lot less of an impactful solvent to use than some of our other organics. And for my sustainability and environmental majors, another thing that we might talk about, I encountered this in a previous part of my life, sorbed phase in environmental work. So phases we tend to talk about, at least in chemistry, we tend to talk about them mostly being as one of several multiple solid phases, or potentially the liquid state being a phase in and of itself, and the gaseous state being a phase in and of itself. But a lot of times in environmental or other field work, you have to think beyond that. Here we have, let's say we've got something that has spilled into the groundwater, into the aquifer, and we're looking at, you can have a water phase with a little bit of dissolved stuff in it. You can have a really dense dissolved phase, and you can have this acronym here, NAPL, stands for non-aqueous phase liquid. So you can actually have, think of this as like an oil sitting in the aquifer, and it can be separate from the groundwater. Now, both the groundwater and the oil here are liquids. They're the same state of matter, but they're definitely physically distinct phases. You have a NAPL phase, and you have a water phase that could also have a dissolved and a near clean or a less concentrated version. You could also have vapor phase in your soils too, and that can become a concern in remediation efforts. Okay, so back to the mathing of our chemistry course a little bit. So this Clausius-Clapeyron equation, so this is the basic form of it, right? That pressure is A times, and this is your Euler number, E. So it should be available to you on your calculator, and you should have done exponential functions by now. And E is raised to the negative delta H, vaporization, divided by R, that's our typical gas constant, T is our temperature in kelvins. Let's see. So So our delta H's that we're going to talk about, I'm going to talk about two different ones. Delta H of vaporization, and then I'm separately going to talk about delta H of fusion. So heat of vaporization, heat of fusion. What these are is that, and I'm going to talk about it on another slide, if we graph it, how it plateaus off and doesn't change the temperature as we add a little bit more heat in order to break through those phase boundaries. So here P is the vapor pressure that we're going to measure. Vapor pressure. The A is a fitting constant. We often have to do this is because we can say that the pressure is proportional to that, but then we need a constant of proportionality. All right, so let's solve for. Let's see what we can do here. Now we want to solve for the T really. So if I've got an exponential and I want to get this power down, that's going to require me to use a natural log. If you are not familiar with natural log, with the ways to work natural logs and to solve equations with exponentials and logs, I do need you to take that to the math lab and just go in there saying, I'm going to need some help. Crisp is on about the maths again, and teach me how to do natural logs and exponentials. So come to me if you want help with, I'll point you in the right direction. But I think the math lab will actually probably do a better job than I do. They teach math all day long, every day. So that would be my first choice, but you can certainly come to me to ask about it too. I don't mind trying to help where I can. So what I'm doing is I'm taking a natural log of both sides in order to linearize this equation. So LNP over here, now rules of logs here, basically taking the ln of the A and I've moved it out to the back, and this negative came down. This is what was the exponent that I put in parentheses up here. Ln E, those are reciprocal functions, and so now we have just what was the exponent. And so what I'm going to do is I'm going to put in, let's do it in purple this time. I'm going to put in another parentheses here. And it's not really a great parentheses. Just stay with me for a second. So what I want to do is I want to think of that negative delta H over R. It's kind of like, so that's like my M in y equals mx plus b, right? So this is my y, right? And this is my m, and then my, now 1 over t, you'd have to be careful and you'd have to plot reciprocal temperature instead of just temperature. That's my independent variable, my x. And now I've got plus b. So now I have a linearized form of this, and it's much easier to manipulate and try to tease out the variables from this. We can do several things, like we can look at 2 different temperatures. And so this is how the delta H of vaporization is often determined by dividing an original of this by at one pressure and another one at another pressure. Just write the same thing underneath it. So you've got P2 over P1, and then take those natural logs, and so you end up with this form right here. And so this form is used to, well, let's see, I can measure that temperature, and I can measure that temperature, or determine them in my experiment, and I can measure the pressures that happen. Well, doing that leaves R as a constant. We know that. So that leaves this right here to determine the slope of a line. And so if we do that, we can use that to determine the delta H of vaporization for a system. And okay, so getting back to more pragmatic matters, which you're likely to see in classwork and then probably on the exam, is one of these. We call it a heating curve, right? So let's look at what we got here. So we could do time. I'm going to change that because I don't want it to be in time. I like for this to be in, let's say, thermal energy. I'm just going to put an E, and I'm going to say let's measure it in joules instead. So joules of energy, that's supposed to be a J. Y'all just believe me on that. It's really hard to write with a mouse. That's a J. That's a J. What's happening here is as we apply more energy, going to the right on the x-axis, we're applying more energy. You could do energy per unit time. I think that only complicates it. But if you apply more energy for a given system, let's say for the A to B segment here that we have a solid. So we're measuring the temperature of that solid. As I apply more energy on the x-axis, y-axis, my temperature goes up. And we can actually determine a slope on this. And so the C, the specific heat, right here, the specific heat gives us the slope of this line. And so as we change the amount of heat added, we can increase the temperature. Now, eventually, though, it does this weird behavior. Segment B to C, you're still increasing the energy going into the system, but your temperature stops increasing. So remember that energy and temperature are not the same thing. We can increase thermal energy here and see no increase in temperature. So, for instance, if this were water, so if this were H2O system, and let's say at 1 atmosphere, we'd have ice, and so ice can be colder than 0 C, so maybe we have ice at -5 C here. We start adding some thermal energy, and the temperature starts going up, -4 C, -3, -2, -1 C, and then it gets to 0 C. At 1 atmosphere, at 0 C, that's the melting temperature for H2O. So we continue to add thermal energy, but our temperature stays at 0 C, stays at 0 C, stays at 0 C, until all of our solid H2O has changed to liquid H2O, still at 0 C. Then, if we continue to add thermal energy, now the temperature will start going up again. This works again, MC delta T. Now, be careful because the C for solid H2O is different than the C for liquid H2O. So this slope might well be different for segment CD than it is for segment AB. But you do get a slope, you get a similar behavior as you increase thermal energy, temperature is going up again. Uh-oh, wait, something's changed. Now we get a new flat line where we're still increasing energy, but temperature is no longer going up. Well, that is a new phase transition. So this first B to C is a phase transition that we call heat of fusion. That is changing. Heat of fusion is defined. I don't like the term either. I'm sorry, but they're not going to change it because I don't like it. Heat of fusion is the change, the heat required to change a given mass at, or given moles. I think we do this one usually in moles and molar values. To change a given amount of solid to liquid at the melting point of that material. Similarly, the heat of vaporization is the amount of energy required to move a given amount of material from the liquid phase to the gas phase at its vaporization temperature, its boiling temperature. All those phase diagrams we did earlier with weird different phases, I don't intend to ask you about those for this course. You're only going to see these questions with a normal ambiguous which solid we mean, just a solid and a liquid and a gas. And this is another sort of way you'll see it practice. Probably we'll see this one in class when we work on this. So how much energy in joules would be required totally? So we know we've got a kilogram block of ice and it's at -2 C. I want to know how much energy to cause it all to be steam. That's the sort of question you should be able to work out. So the next homework will be, the next video lecture will be on solubility. To prepare for that, there's our reading sections 11.1 and 11.2, but if it is possible that you might not be all the way okay with solution calculations from Gen Chem 1. So here's some reference back 3.3, 3.4, and 4.5. That's not 3.5, but 4.5. And also my my old recorded 1121 lecture and PowerPoint are also available in the review section. Lecture 7 particularly might be useful. So please review what you might need. We're going to be talking about molar, molal, all the different types of concentration units and how to calculate them. Well, we won't spend a whole lot of time on the how to calculate them because that's kind of Chem 1 material, but let me know if you need to review that more. So I'm going to expect you to be able to go forward with those and talk about different solubilities and what different molal concentrations are going to do to things with their temperatures, melting points, and stuff like that. All right, see you in class.